Next, we're going to talk about percent yield. And percent yield is a way for us to indicate how successful a reaction was or how efficient it was, especially in industry or in a laboratory setting. And there is a formula to calculate this. It's the actual yield over the theoretical yield. Of course, any percentage you take times 100, and that is percent yield. Now, we've done a different percentage in the past. We've done percent error. And in percent error, we wanted a very low number. In percent yield, we want this value to be a high percentage, indicates more success. So a higher percentage is better. There are some terms that go along with this. The theoretical yield is the maximum amount of product that you could calculate from a stoichiometry calculation. And I want to emphasize that it's a calculated value. You do this on paper. The actual yield is produced in a reaction in the lab. So you have to get this in the lab, or it would be given in the problem if you can't do a lab. Actual yield can be lower than theoretical yield if there are competing reactions that would use up some of your reactants. If you end up with an actual yield that's bigger than theoretical yield, it would be because it's impure. That would be the only way. So these two are describing actual yield. So again, the actual yield is measured in a lab, or it could be given in a problem. Okay, that's possible, given to you. And the theoretical yield, you're going to calculate that on paper. Here's an example. It says, with this reaction, what mass of phosphorus is needed to produce 85 grams if the reaction has a 64.9% yield? Okay, so I'm going to organize my thoughts here a little bit. I have a problem that says it's 64.9% yield. Also in the problem it says what mass of P4. So what mass produces 85 grams? I'm going to start with this given right here, 85 grams of PF3, and I'm going to convert grams to moles. Now this substance has 1 phosphorus and 3 fluorine, and the total molar mass here, phosphorus is 31, fluorine is 19, and so the molar mass of this is 88.0. Alright, next I'm going to convert from moles of PF3 to moles of what I'm looking for, which is P4. The mole ratio is 4 to 1. Alright, and the problem asks for me to give this answer as a mass. So I'm going to convert from moles of P4 to grams of P4. Now phosphorus, just one atom of phosphorus has a mass of 31, so 31 times 4 is 124 grams. Moles cancel out. So when I do my work here, 85 on the top times 124, I divide by 88 and divide also by 4, and I get 29.9. Now this is how much would be required to produce 85 grams. But remember that it only has 64.9% yield. So I have to actually start with more of it in order to get a total of 85. So I could have done this calculation up front by modifying 85, or I can do it at the end. It doesn't really matter. But what I want to do is I want to find out, well, how much more would I have needed, since I know that the reaction doesn't completely convert it over. So what I'm going to do then is take this number and I'm going to divide it by 0.649, and I'm getting that from the percent yield. So 29.9 divided by 0.649. This is going to tell me what I would have needed to have 46.1 grams of P4. Now, like I said, you could have done this work in the beginning. You could have taken the given here and divided by 0.649, and that would have given, I can find out what that answer is, 85 divided by 0.649, and that would have been 131 grams. You would have plugged that number in here, and then the final answer that you would have gotten from that should also be 46.1. Either way, the difference is the same, I guess, is what I'm trying to say. Whatever makes more sense for you. Now that's kind of a unique problem that I haven't typically seen a whole bunch of examples like that, but it's an application of percent yield. Here we have given 45.8 grams of K2CO3. React with excess of this, which means that we already know that this reactant was limiting. And we produce 46.3 grams of this product. So we want to find the theoretical yield and the percent yield. So this number right here is the actual yield. Okay? Percent yield takes the actual yield over the theoretical yield. Well, I know that the actual yield is 46.3, so now I need to find out what the theoretical yield is and then take that times 100. Alright, so I'm going to start with this number here, and I'll do a stoichiometry calculation to find out the theoretical yield of that product, assuming that I have excess of this one, so it's not going to run out. Okay, convert grams to moles. K2CO3, 2 potassium, 1 carbon, and 3 oxygen of 99.1. Alright, so grams cancel out there. And then we're going to convert from moles of one substance to moles of another. Moles to moles. This is called the mole ratio. K2CO3 and KCl. This is a 1 to 2 mole ratio from our coefficients here and here, and that cancels out. Last step would be to convert from moles of KCl to grams of KCl. And let's see, 1 potassium, 39.1, plus 1 chlorine, 35.5, is 74.6. Cross that out. Now I'll do the rest of my math here. So 45.8 times 2 times 74.6 divided by 99.1. And I get 68.954. So really for, let's see, 3 significant figures, it would be 69.0 grams of KCl. Well, that is the theoretical yield. That's how much I'm supposed to get of that compound according to what I started with. And I'm going to plug that one in. If you remember, I had written this out ahead of time. I'm going to plug this number in, the theoretical yield, right up here in the denominator. And then I'll calculate it. So 46.3 divided by, oops, I'm sorry, I wrote the wrong number in here, 69.0, and I get, and times 100, 67.1% yield. And that is, whoops, that is your final answer.